In this video, we'll talk about the product and quotient rules for computing derivatives. Recall that the sum and difference rules showed us how to compute the derivative of a sum, or a difference, of differentiable functions. The derivative of the sum is the sum of the derivatives, and the derivative of the difference is the difference of the derivatives. So this leads to some natural questions. How do we compute the derivatives of a product, or quotient, of two differentiable functions? Is it just the product or quotient of the individual derivatives? And the answer to that second question is a resounding no. The product and quotient rules do tell us how to compute the derivatives of the product and the quotient. And the product and quotient rule will tell us how to do that by making use of the derivative of f and the derivative of g. But it isn't as simple as just taking the product of the two derivatives or the quotient of the two derivatives. There's more to it than that. This is the product rule. If f and g are differentiable at x, then their product is also differentiable at x, and this is how you compute it. The derivative with respect to x of the product f at x times g at x is equal to f prime at x times g at x plus f at x times g prime at x. The way I like to say this is the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. We're not going to prove this now, but let's take a look at how we might use it in some examples. Here's our first example. Compute the derivative with respect to x of the product x squared times e to the x. So we're going to use the product rule. This is a product, so it makes sense that we use the product rule. The derivative with respect to x of the first function, x squared, times the second function, e to the x. This is equal to the derivative of the first times the second plus the first times the derivative of the second. And these derivatives we can compute. The first derivative is the derivative of x squared. That's a power function, so we use the power rule. That's 2x. And the second derivative is the derivative with respect to x of e to the x, which of course is just e to the x. So that tells us that the derivative of x squared times e to the x is 2x e to the x plus x squared e to the x. Notice that we started out with a product of two functions, x squared and e to the x. And the way we computed the product was by computing the derivative of the first function, the derivative of x squared, and the derivative of the second function, the derivative of e to the x. So we do compute the individual derivatives of these functions, but we don't just simply multiply them together. Instead, we combine them in what might seem like an unusual way. We multiply the derivative of the first function by the second function, and we multiply the derivative of the second function by the first function, and then we add those two together. Let's do another example. The derivative with respect to x of x times the square root of x. So let's just rewrite this. The derivative with respect to x of x times the square root of x. So we have a product of two functions, so we're going to use the product rule. So again, it's the derivative of the first function times the second function plus the first function times the derivative of the second function. Now each of these derivatives we can compute. The derivative with respect to x of x is just 1. And what about the derivative with respect to x of the square root of x? Well, let's just remind ourselves here that the square root of x is equal to x to the 1/2. So the derivative with respect to x of the square root of x is the same as the derivative with respect to x of x to the 1/2. And now we can use the power rule. You bring the exponent down, Then you multiply by x and decrease the exponent by 1. So 1/2 minus 1. What's that going to be? That's 1/2 times x to the minus 1/2. So now we can put all of this together, and we have that the derivative with respect to x of x times the square root of x is equal to 1 times the square root of x plus x times 1/2 times x to the negative 1/2. This is equal to the square root of x plus x over 2 square roots of x. Now actually x over the square root of x is the square root of x. So this is the square root of x plus the square root of x over 2. So we have a whole square root of x and half of a square root of x. So if you put all of those together, you end up with 3/2 square root of x. Now, in fact, you don't have to use the product rule for this one. There's another way. And what is this other method? Well, you don't have to write it as a product. X times the square root of x is really a power function, because this is x times x to the 1/2. So we can just add the exponents together to get x to the 3/2. So if we want to differentiate x times the square root of x, another way to do that is just simply differentiate x to the 3/2 using the power rule. And what do we end up with? We end up with 3/2 times x, and then we decrease the exponent by 1. So we have 3/2 times x to the 1/2, which of course is 3/2 times the square root of x, which is what we got the other way. There's often more than one way to do a problem, and there is no one right way. There are multiple ways to come up with the same correct answer. Let's compute the first and second derivative for the function f at x equals x times e to the negative x. F at x equals x times e to the negative x. So the first derivative, f prime, will be obtained by differentiating this product. The derivative of x times e to the negative x. So we use the product rule. The derivative with respect to x of x times e to the negative x. That's the derivative of the first times the second, plus the first times the derivative of the second. And each of these derivatives we can compute. Again, the derivative of x with respect to itself is just 1. And here we're using the more general version of the exponential rule. Recall that the derivative with respect to x of e to the kx is equal to k times e to the kx. So we're using this rule with k equals -1 in this case. So that tells us that this derivative is negative e to the negative x. So if we put all of that together, we have that f prime of x is equal to 1 times e to the negative x plus x times a negative e to the negative x, which we can also write as e to the negative x minus x times e to the negative x. If we want to, we can factor out that e to the negative x and write this as 1 minus x times e to the negative x. And this is our first derivative. Okay, well, if we want to compute the second derivative, f prime prime, that's just the derivative of the first derivative. So that's the derivative with respect to x of f prime. Well, we've just computed that. So that's the derivative with respect to x of 1 minus x times e to the negative x. And again, it's a product, so we use the product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Okay, well, the derivative of the first, what's the derivative of 1 minus x? Well, the derivative of 1 is 0, minus the derivative of x is minus 1 times e to the negative x, plus 1 minus x times the derivative of e to the negative x. But of course, the derivative of e to the negative x is something we just computed right here. In fact, let's just highlight that. The derivative with respect to x of e to the negative x is negative e to the x. So we're differentiating the same function here again. So this is going to be negative e to the negative x. So we can simplify this, and this will be equal to 0 minus 1 is a minus 1 times e to the negative x. And then we have a minus 1 minus x times e to the negative x. And if we factor out the e to the negative x, we'll be left with a minus 1. And then this term here, we run the minus sign through. So there will be a minus 1, and then minus a negative x is plus x. So that gives us e to the negative x times x minus 2. And this is our answer for the second derivative. Our next theorem is the quotient rule, and it tells us how to compute the derivative of a quotient. So what is the statement of the quotient rule? Well, we start with f and g, which are differentiable at x. Then the quotient rule tells us that f at x divided by g at x is also differentiable at x, and the derivative of f at x divided by g of x can be computed in the following way. F prime at x times g at x minus f at x times g prime at x divided by g at x squared. The way that I like to say this is that the derivative of this quotient f divided by g is equal to the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. Now this formula is a little bit more difficult to remember, but the numerator is the same as it is with the product rule, except that the plus becomes a minus. And then we just need to remember to divide by the bottom squared. Another way to think about this, if you have difficulty remembering the quotient rule, is that you can rewrite a quotient as a product. So note that f at x divided by g at x is equal to f at x times 1 over g at x. So you can always write a quotient as a product. So if you have difficulty remembering the quotient rule, very often you can solve that problem by expressing it not as a quotient, but as a product. As long as you can compute the derivative of 1 over g to the x, you can just use the product rule. And we'll see that with some of our examples. Let's compute the derivative with respect to x of this quotient, x squared divided by x squared plus 1. So the derivative with respect to x of x squared over x squared plus 1 is equal to, well, it's the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. Now all of these derivatives that are here we can compute. The derivative of x squared, that is 2 times x. And the derivative of x squared plus 1, that's also 2x. In fact, that's 2x plus 0, because the derivative of 1 is 0. So that tells us that the derivative is 2x times x squared plus 1 minus x squared times 2x, divided by x squared plus 1. Quantity squared. The numerator can be simplified. So 2x times x squared is 2x cubed plus 2x times 1 minus x squared times 2x, which is another 2x cubed. And all of this is divided by x squared plus 1 quantity squared. And the first 2x cubed cancels with the second 2x cubed. And we're just left with 2x divided by x squared plus 1 quantity squared. And so we were able to compute the derivative of this quotient using the quotient rule. Here's another example. Compute the derivative of the quotient e to the x divided by x cubed. So what is this going to be equal to? Using the quotient rule, we can say that the derivative with respect to x of e to the x over x cubed is equal to the derivative of the top times the bottom minus the top times the derivative of the bottom. And all of this is divided by the bottom squared, which is x cubed squared. Now once again, we can compute all of the derivatives that we see here. The derivative with respect to x of e to the x, that of course is e to the x again. And the derivative with respect to x of x cubed, this using the power rule, is 3x squared. So that tells us that this derivative is e to the x times x cubed minus e to the x times 3x squared. So just so we're clear, this e to the x is the derivative of the top, and this 3x squared is the derivative of the bottom. And then we divide all of this by the bottom squared, x cubed raised to the 2. If you have an exponent raised to an exponent, then you multiply the exponents together, so that's x to the 6. And this one, we can factor out the e to the x, and we'll have e to the x times x cubed minus 3x squared divided by x to the 6. Now notice you can actually factor out more than just the e to the x. You can factor out an x squared. We have an x squared here, and this x cubed you can write as x squared times x. So you can factor out an x squared there as well. So let's just go ahead and do that. So this is going to be equal to, let's factor out the x squared, so it'll be x squared e to the x times x minus 1, and this is divided by x to the 6. Sorry, this should be x minus 3, so this should be a 3 here. While I'm at it, let me just fix this bracket. Okay, so it's an x minus 3 because we have a 3 right here, so this should be a 3 as well. Okay, so notice that we have an x squared here in the numerator and an x to the 6 in the denominator. So this x to the 6 we can rewrite as x squared times x to the 4th, and then we can cancel out our x squareds. So this x squared cancels with that x squared, and we're just left with x to the 4th in the denominator. So this will be equal to, oh no, this should be a different color. This will be equal to e to the x times x minus 3, and we'll divide all this by x to the 4. And that's our answer. Now, in this particular case, we didn't need to use the quotient rule, because you can also write e to the x over x cubed as a product. So note, e to the x over x cubed is equal to e to the x times x to the negative 3, because 1 over x cubed is equal to x to the negative 3. So we can actually write this as a product and get the same answer. Let's just verify that. So the derivative with respect to x of the quotient e to the x over x cubed is equal to the derivative with respect to x. We can just rewrite this as a product, e to the x times x to the negative 3. And then this will give us, using the product rule, the derivative of the first times the second plus, because we're using a product rule now, the first times the derivative of the second. And of course these derivatives we know how to compute. The derivative with respect to x of e to the x is e to the x, and the derivative of x to the negative 3 is negative 3 times x to the negative 4 using the power rule. Now this negative 3 right here, that's where the minus sign comes in the product rule, as you'll see, because when we simplify this we'll get the same thing we got before. So this derivative is equal to e to the x times, and let's just write it as 1 over x cubed now, plus e to the x times negative 3 over x to the 4. And let's factor out that e to the x. We'll have e to the x times 1 over x cubed minus 3 over x to the 4. Now we want to add these together, or rather subtract them, so we give them a common denominator, which in this case means multiplying by x over x on the first one. So then we'll have an x to the 4th in the denominator. And so this will give us e to the x times x minus 3 over x to the 4. And as you can see, e to the x times x minus 3 over x to the 4 is the same thing that we got before. And notice that there's a minus 3 here, and that minus 3 came from the power rule, and so that's why there was a minus there. So the minus sign in the quotient rule comes from the fact that when you turn it into a product, you're going to end up with a negative exponent. Let's do another example. The derivative with respect to x of x squared plus 1 divided by x. So again, we just use the quotient rule. So it's the derivative of the top, which is x squared plus 1, times the bottom, minus the top, which is x squared plus 1, times the derivative of the bottom, divided by the bottom squared. The bottom squared. And of course we can do these derivatives. Let me just move this over here a little bit. So this derivative, the derivative of x squared plus 1, that's going to be 2x plus 0. And here we have just the derivative of x. So this one is going to be just 1. So we'll end up with 2x times x minus x squared plus 1 times 1, and all of this is divided by x squared, which is equal to 2x squared minus x squared minus 1 over x squared. Now notice that there's a minus sign here, so this minus sign right here is that one, and it's also that one. We distributed it. We distributed the minus sign from here throughout here. Okay, so now we can simplify. 2x squared minus 1x squared is just going to give us 1x squared. So we'll have x squared minus 1 over x squared, which, if you wanted to, you could rewrite as 1 minus 1 over x squared, if you preferred. The reason I'm doing that will become apparent in a moment, because this is yet another example of where you can get around using the quotient rule. So there are a couple of different ways we can think about this. So note, we can rewrite x squared plus 1 over x as x squared over x plus 1 over x. And we can simplify that first term, that's just x, plus, and let's write 1 over x as x to the negative 1. So if we want to differentiate this quotient, x squared plus 1 over x, instead of using the quotient rule, we can write this as the derivative with respect to x of x plus x to the negative 1, and just differentiate term by term using the power rule. So the first one, well, let's just write it out. The derivative with respect to x of x plus the derivative with respect to x of x to the negative 1. Now the first one, the derivative of x, is just going to give us 1. And the derivative of the second one, that's going to give us minus 1 times x to the negative 2. So our derivative with respect to x of x squared plus 1 over x is equal to 1 minus x to the negative 2, which is 1 minus 1 over x squared, which I think is what we got before. Yes, it is. 1 minus 1 over x squared. So we can see that we have it here, 1 minus 1 over x squared, and we also have it here. It's very often the case that you can solve these problems using more than one method, and there is no one right method. Whichever method works for you is the right one to use.